Hello, good morning. Iñaki gave a really nice introduction to these kinds of topics. What I want to talk about this morning is heterogeneity and variance. Variance is a powerful measure of the differences between individuals within populations. And what I'm going to talk about, what you're going to see going very quickly, is partitioning of variance and a new approach to partitioning variance for multiple factors, a couple of examples, and in particular, a new issue that comes up about mixing distributions and why you should consider them to be your friend. So, a heterogeneous population is a mixture. It has some set of groups within it. Those groups appear in different proportions within it. Each group has a mean and a variance, as well as other statistics, for whatever demographic outcome you are interested in. So think of longevity or healthy longevity. And that set of proportions within the population is called the mixing distribution, and that is the tool that allows you to partition the variance. The population, which is made up of these heterogeneous groups, has an overall mean, which is the weighted mean of the means within the groups, and it has an overall variance, which has two terms, the weighted mean of the within-group variances and the weighted variance of the within-group means. Well-known formula in statistics. And so you have this ability to partition variance in a heterogeneous population into within group and between group components. There's a, do anything? Quantity called the variance ratio, which is just the fraction of the overall variance contributed by the between group variance due to heterogeneity. You can do this for a variety of demographic outcomes, including longevity. You can get all of the necessary moments from Markov chain models. Shout out to Gustav Feitinger, who is here, because in 1971 he wrote a whole book talking about, among other things, how to look at demography with Markov chains. People tend to think that longevity and fertility are somehow different, but they're not. You can calculate all of the necessary moments for heterogeneous populations in terms of lifetime fertility and in terms of healthy longevity with methods, some of which provide nice answers to some of the issues that Iñaki raised this morning. But how many factors? Well, we all got a bag this morning which has age, sex, and education as factors, but almost all studies only look at one factor at a time, education or age or sex, even though we all know that multiple factors are operating. And so what would be nice is to be able to look at the variance due to each factor operating simultaneously and to the interactions between them. Possibly, if it's like previous talk that I know about, there might be an example of this later on in this conference. Yes? No? Maybe? I don't know. So here's what this method does for a case with two factors, factor A and factor B. And what you're interested in doing is taking the between group variance and breaking that down into a component due to factor A, a component due to factor B, and a component due to their interaction. In order to do that, you have to define the mixing distribution within the population, the proportions that all those combinations of factors occur in. And when you took statistics, they probably told you when you're designing an experiment, always have the same number of experimental units in each treatment combination. There was a reason for that. you have to have one of two types of mixing distributions to be able to partition variance in this way. One is flat, equal proportions for everybody. It's like an experiment. The other one is a proportional or rank 1, which can have non-flat distributions, but has to just be based on the marginal distributions. They ask different questions. They answer those questions. They're your friends. Now, no, I'm not going to go through, because you can't do that in this short time, but there are some equations to do this for arbitrary numbers of factors. Let's consider a two-factor case. This is sex and race longevity in the United States as of 2020. The reason that I picked these factors is just because they're easily accessible. So there's 5 racial groups defined in the US Census, and there are 2 sexes. And so here is a table of the mean longevity, the life expectancy for each racial group, males and females. Nothing surprising to anyone in this audience in this table. Here's a table of the corresponding variances. Nothing surprising, because there's not really a particularly great pattern in it, but there they are. And when you do this, you can look at 2 different mixing distributions. One is a flat mixing distribution. Every race occurs in the same proportion, every sex occurs in the same proportion. Or these are the racial groups in proportions corresponding to their representation in the US population as of 2020. It's mostly non-Hispanic whites and Hispanic, American Indian and Alaskan Natives, almost nothing, non-Hispanic Asians, a small amount. So this is saying that you really care more about Hispanic and non-Hispanic whites, and you don't care much about American Indians and Alaskan Natives. So this is the breakdown of the variance components for this, with the flat mixing distribution on the left and the rank 1 mixing distribution. You see the component of variance due to race, due to sex, due to the interaction. It's very small in both cases. The overall between group variance, which is the sum of those 3. The amount of variance due to the stochastic outcome of probabilities of survival or dying within a group is much bigger than any of them. The variance ratio, about 12% of the variance, is due to heterogeneity. In this case, about 6% in this case. When you shift here, the racial component gets much smaller, because the races are now overwhelmingly just the 2 most important races, and in the flat mixing distribution, you're treating all the races equally. So you can do this for 3 factors. You can do it for any number of factors. So this is longevity for sex and race and state of residence in the United States. Turns out that the differences in longevity in life expectancy among US states between 73 years and 80 years is totally comparable to the differences that we see in terms of differences between sexes and differences between races. For the year 2000, I was able to find life table data, 40 US states, 2 races, in this case just white and black, and 2 sexes. The other states, there's not enough data for them, so the Census Bureau didn't include those. So here are the variance components. We have a component due to sex, due to race, due to the state of residence. We have 3 two-way interactions: sex by race, sex by state, race by state. Those interactions are all relatively small. We have a 3-way interaction, contribution to variance of the 3-way interaction between race, state of residence, and sex, and it's also small. The overall sum of that is the between group variance due to heterogeneity. There's a very large component due to stochastic outcomes of survival within the groups, and the variance ratio, again, is about 6%. So the conclusions that I would like you to take away from this is, first of all, it's useful to think about populations that are heterogeneous, think about them as mixtures, and to apply techniques to break down variance into components due to the heterogeneity, due to stochastic outcomes within the groups. It's now possible to do multiple factors operating at the same time and their interactions. You can do it for longevity, for lifetime fertility, healthy longevity, lots of other variables. And in the vast number of examples considered so far, interactions only make a small contribution. I bet that there's cases where it will make a bigger contribution, and that will be really interesting to find. And variability and heterogeneity in lifetime fertility hasn't been looked at anywhere near as much. But we have the tools to do it, and it seems like in some cases it may behave a little bit differently with more contributions from heterogeneity and interactions, but it's too soon to tell. So that's a thing for the future. So thank you, and I will be happy to take questions.